we have derived the formula of total energy in terms of the Rydberg constant and the atomic number and principal quantum number. It was derived in the unit of joule. Now, energy can also be expressed in terms of electron volt. So, now we will see what is the formula of energy if we measure in electron volt. So, this is the formula of energy in joules. We know that 1 electron volt is equal to 1.6 into 10 to the power minus 19 joules. So, if this many joule is equal to 1 electron volt, then 2.18 into 10 to the power minus 18 joule will be equal to this electron volt. So, this comes as 13.6 electron volt. So, we can write the formula of total energy as minus 13.6 into Z squared by N squared electron volt. This is a very important formula because for hydrogen atom, we know that hydrogen atom has 1 electron, number of electrons equal to 1. So, for the ground state will be N equal to 1, right. So, and for hydrogen atom, its atomic number is also 1. So, if Z equal to 1 and N equal to 1, we get E equal to minus 13.6 electron volt. So, this is the energy of ground state of hydrogen atom. Ground state energy of hydrogen atom. Okay. Now, we have calculated the absolute term for energy. Now, how will we calculate the energy difference between two energy levels? Energy difference between two energy levels. Let's say these are the two energy levels. One is N1 and another is N2. So, this is the difference of energy. Let's say the level N1 has an energy of En1 and the N2 level has an energy of En2. So, the difference between these two energies delta E will be equal to En2 minus En1, right. Now, according to the formulas, we can write En1 as minus RH into Z squared by N1 squared, and we can write En2 as minus RH into Z squared by N2 squared, right. So, what will be delta E? Delta E will be En2 minus En1, that is equal to minus RH Z squared by N2 squared minus RH into z squared by n1 square. So this can be written as RH. So this will be plus. So this can be written as RH into z squared by n1 squared minus RH into z squared by n2 square. Now if we take RH as common, if RH is common and also z squared is common, then we can write 1 by n1 square minus 1 by n2 square. So this is the term for energy difference. I'm sorry, this is delta E. This is delta E. So this is the formula for the difference in energy levels. Okay. Now when we were calculating the terms of energy, we saw that energy has a negative sign. Now what is the significance of the negative charge? Significance of negative charge. So it is considered that when an electron is revolving around the nucleus in a certain orbit, then the force of attraction of the nucleus acts on the electron. But when the electron is taken infinitely away from the nucleus, that is, let's say in an orbit n equal to infinity, if we take the electron infinitely away from the nucleus, then there will be approximately no force of attraction of the nucleus acting on the electron. So it is considered that a free electron, that is an electron which is infinitely away from the nucleus and is at rest, it will have a higher energy than an electron which is moving around the nucleus in a circular orbit. So the energy terms are calculated with respect to the energy of the free electron at rest. So the statement is the energy of an electron revolving around the nucleus in an orbit is considered to be less than the energy of a free electron at rest. What is a free electron at rest? A free electron at rest is an electron which is infinitely away from the nucleus. Okay. Now let's consider the free electron is at n equal to infinity. Okay. Then what is the energy term? En equal to minus RH into Z square by n square, right? So, for n equal to infinity, E infinity can be written as RH in minus RH into Z squared by infinity, right? If n equal to infinity, then this term will be infinity. Now, if the denominator is infinity, then E infinity will be equal to 0. Therefore, the energy of a free electron at rest is 0. Okay. So, what we have seen, that the energy of an electron revolving around the nucleus in an orbit is considered to be less than the energy of a free electron at rest. So, any energy term will be less than this. So, for any electron in the nth orbit where n equal to 1, 2, 3 or any number, En will be always less than E infinity, right? And E infinity equals to 0. So, En will always be less than 0. Therefore, En will be negative, right? So, for any orbit, the sign for energy will be negative, but its magnitude will increase with the decrease in n, right? So, the most negative value of energy is given by n equal to 1. Okay. So, we have studied the significance for the negative sign of energy. Now, before starting the Bohr's model, we had seen some formulas about the line spectrum of hydrogen. We had expressed the line spectrum of hydrogen in terms of wave number. Now, by Bohr's model, we can explain these formulas in terms of energy as well. So, what do we know? We know that when an electron absorbs energy, it moves from the lower energy level to a higher energy level, or from ground state to excited state, and from this we get the absorption spectrum. And when an electron reaches a higher energy level or an excited state, it can emit radiation, or it can emit energy in form of radiation. So when it emits energy, it will come back to a lower energy state, or it can come back from the ground state from an excited state. So this gives us the emission spectrum. So with the terms of energy, we can express the emission spectra or absorption spectra, and we can explain the line spectrum of hydrogen. So explanation for line spectrum of hydrogen. So we see that suppose this is n equal to 1, this is n1 and this is n2. When an electron absorbs energy, it moves from lower energy level to higher energy level. This is absorption. And when it emits energy, it comes back from the higher energy level to the lower energy level. This is emission. Now let's consider the initial orbit as initial orbit is Ni and final orbit is Nf. For Ni, the corresponding energy will be Ei, and for Nf, the corresponding energy will be Ef. Now, we will explain the energy terms and the wave number in terms of the Bohr's model. We will explain the hydrogen spectrum from the Bohr's model in the next lecture. Thank you.